if you think about how the course has been going, what we've done so far is we've had, right, if we think about our arc of our course that I like to talk about all the time, which is that we've had the, from the sort of smallest bits, like what's an atom like, then how do atoms connect to make molecules, and what are molecules like, and now we're looking at sort of the properties of molecules. So what we just finished up was intermolecular forces, which is basically how does the structure of a molecule affect its physical properties, right? So we looked primarily at boiling point and solubility as a way of analyzing, as a way of looking at how the structure of a molecule affects its physical properties. And now we're going to look at chemical properties, so reactivity. And what we're going to be doing is we're going to be looking at how does the structure of a molecule influence its reactivity. And we're going to be looking specifically at acidity as a stand-in, all right? Because acid-base chemistry is something that you are probably, of all the types of reactivity and things like that, the most familiar with. Because, it's, well, honestly, it's something that's you've been looking at since high school, in the middle of high school somewhere, or at least the concepts of acids of acidity. So we're going to look at that in detail a little bit more. All right, so we have talked in your sort of chemistry education about acidity and what it means, right? So if we think about our classic definitions of acids and bases, an acid, according to the Bronsted-Lowry, which is maybe the most common theory that we use, is a hydrogen ion donor, and a base is a hydrogen ion acceptor. And when it comes to the, how acidic something is, we've kept it very simple up till now, which is we said there are strong acids and weak acids. And the way we tell them apart up till now has been, well, there are 6 common strong acids, and you needed to memorize them, and all the rest are weak acids. But we sort of ignored the how come part, like why are strong acids strong? Why are weak acids weak? And so that's where we are going to spend our time now. So just a reminder that the difference between strong acids and weak acids has nothing to do with things like concentration, but everything to do with ionization. So strong acids like hydrochloric acid in the picture ionize completely when we put them in solution. So that means when I take hydrogen chloride, which is a gas, right? It's a covalent compound. And if I bubble it through water, it dissolves and I get H plus and Cl minus, or H3O plus. I do want to point out that I'm going to jump and use H plus and H3O plus kind of interchangeably depending on what suits my needs. All right, so it doesn't really matter if I say H plus or H3O plus. I'm going to use them interchangeably, again, depending on the context. So that's the thing, is that strong acid ionizes completely in water. There's no actually molecules of the acid left. There's only the ions. All right. In contrast, weak acids only ionize a little bit, right? It's an equilibrium process, if you recall. And so, for example, if I take HF in a beaker, and to be fair, there's something wrong with this, with the picture in the slide, which is that HF dissolves glass. So that beaker would have to be plastic. But if I have HF in water, you'll see that mostly I actually have molecules of HF that are left. They're unionized. They stay together. And only a little bit of it ionizes to give me H3O plus and F minus. So that's the difference between a strong acid and a weak acid, is strong acids ionize completely, weak acids ionize a little bit. And what we're going to try and look at now is, well, why does this happen? All right. So again, I want to give you some refreshers on acid-base chem. Weak acids ionize partially, and that's reflected in an equilibrium system. What is that? Remember, an equilibrium is a dynamic equilibrium, which means when we are at equilibrium, the forward and reverse reactions, as illustrated here, are happening at the same rate. And we can write an equilibrium expression for this, which is down here. So K, and it's in this case, it's a Ka, right? Because it's an acid. And the Ka is a ratio of products over reactants. And the value tells us how much does that acid dissociate, essentially, right? So if the fraction is small, now acids, the fraction is always going to be less than one, significantly less than one. And so it's going to be a small amount that dissociates. And yeah, there's a typo in this slide, by the way. This should be X, yes, like that. All right. And we typically, so the larger the value of Ka, the more acidic something is. But because these typically are small numbers, 10 to the minus 3, 10 to the minus 5, 10 to the minus 10, they're annoying, in all honesty. And they're annoying to think about. So we tend to use a logarithmic scale to talk about the relative strength of acids, just like we do if we're talking about acidity. So instead of, when we talk about how acidic a solution is, we don't generally talk about how the actual concentration, say, of H3O plus. We typically talk about its pH instead, because it's a much nicer scale to use. We get to use some sort of more sensible or practical numbers. And so we do the same thing with Ka. Instead of often, not always, but often, instead of talking about Ka, we talk about pKa. And so that just means minus log of the Ka. And that takes sort of small numbers and makes them, sort of between, say, 1 and 50 or 0 and 50. So it makes life a little bit easier. So that's where you're going to see. So just like pH, have a smaller value of Ka, it means we have a stronger acid because there's a negative sign in the equation. And so just to give you a sense, the strong acids that we're know commonly, so for example, HI is actually one of the strongest of the strong acids. It has, if you really have good equipment, you can actually measure a pKa for strong acids. We tend not to talk about it because there's no point. When you have, say, a pKa of minus 10, and you think about how this equation works, if you work backwards, it means the value of this Ka is enormous. And so it's so big that we don't even need to think about it as an equilibrium. So, but we can see that the strong acids have very, very low pKa's, so much so that we don't even talk about them. All right. But weak acids have pKa values above 0 and less than 7 or 7. Yeah, about between, say, 0 and 7 or 1 and 7. And so we're going to start looking at why, and we're going to start with the simple ones, with the binary acids, why there's a difference in the strength of these acids. This phrase here is the one that, this is like the most important takeaway from this subject, all right, which is the strength of an acid is determined by the stability of its conjugate base. So what that means is that when we are trying to figure out, based on the structure of a compound, why it is an acid or why is it more acidic than another compound, we actually don't look at the acid itself. We have to look at its conjugate base. And the reason for that has to do with this equation again. Remember that a strong acid, so on the surface, I'm just using a stand-in here, right? Actually, what's the HX? So this would be for a weak acid. But for a strong acid, the equation actually looks almost the same, right? The only difference is not in the products or the reactants. It's actually just in the arrows that we use. And why is that? Well, what that must mean for us is that the difference is in how the reverse reaction happens, right? So this was for a strong acid. And so what it means is for a weak acid, the reverse let's say it competes. I don't know if that was maybe to forward with. But in a strong acid, the reverse reaction so basically what it's saying is that in the case of a weak acid, the reaction of the conjugate base A minus with H3O plus going that way, it's significant in the system, right? In the beaker, basically. But in the case of a strong acid, the reverse reaction isn't. It doesn't matter. So the difference has to be at the level of here, right? Because everything else is basically the same. Yes, I know HA and HA, they wouldn't necessarily be the same thing. But because the difference is in the reverse reaction, right? So the difference between a strong acid and a weak acid is not in the forward reaction. It's really in the reverse reaction. So and going backwards, what do we have? We have the conjugate base and hydronium. So hydronium is the same in both cases. So the difference has to be at the level of the conjugate base. That has to be the issue. So we always have to analyze the conjugate base. And so if we look at, say, HF and HI. So HF is a weak acid. And HI is a strong acid. So basically, what it comes down to is this. F minus is more reactive than I minus. Right? Remember, stability is basically the opposite of reactivity. So when something is reactive, it's not stable. It's willing to do stuff and change. When something is stable, it's not reactive. So the difference, why is HF a weak acid and HI a strong acid? It's because this is more reactive than I minus, basically. F minus is not stable. And so, again, why is that? And the reason, we're going to go through basically a hierarchy of properties to analyze. The first thing that we're going to look at is what is the atom or the ion essentially carrying the charge. And you have to remember that charge density actually becomes a major factor in here. So what does that really mean? So remember that so these are some things I'm saying remember, but you probably don't even know necessarily, is that in order for electrons to go and make bonds, they have to be kind of together. They have to be localized. They have to be condensed in a physical location where they can act together. And if you think about the differences in the halogen ions, right? So from F minus down to I minus, they all have a charge of -1, but there's a significant difference in their sizes. So that means the charge density is going to be different, right? So if we look at the charge density between F minus and I minus, well, we're going to see that this has a relatively high, let's see if I can write properly, high. And down here, then we have a low charge density, which means a low charge density means a low reactivity, and a high charge density means a high reactivity, right? So imagine that, right, the electrons are, we've seen in other places in, say, polarity diagrams, things like that, these charge density maps, right, with the different colors. And so you can imagine that the F minus would be kind of a bright red, right? You have that charge is very concentrated in a small space, so it's easy for it to react. In contrast, the iodide is much, much bigger. So that maybe that one would like a yellow or a green color, so that the charge is much more spread out. And when the charge is spread out, the electrons don't behave in a way, it turns out, that allows them to be reactive. So ultimately, here, the fact that the ions are bigger means that it's less reactive, and that comes down to that difference. And this idea of charge being spread out is really, really important in everything we're going to talk about for dealing with acids and bases, the strength of acids. So we're going to talk about there. I'm going to show you once we introduce all the concepts. Then we're going to talk about how to organize this in terms of a hierarchy of making decisions. All right. So the first one we talked about is ion size. After that, it's the electronegativity of the atom carrying the charge. All right. So and sometimes you're going to see the atoms, the molecules that I'm showing you aren't necessarily acids, but it's a relative discussion. Now, I'm never going to ask you to memorize pKa's. I don't care about that. All right. The kinds of questions that you're going to get are going to be, well, here's, I don't know, 2 or 3 or 4 different compounds, rank them in terms of their acidity and justify them. And so basically that's what I'm going to show you how to do. So here's 2 molecules. They're very, very similar. Neither of them is particularly acidic at all. Really, this is an alcohol. This is methanol. It's not the drinking kind. Don't drink it, you'll go blind. This is methylamine. Also, I mean, don't drink that. It's poison. But you can imagine an acid-base reaction in both cases where it reacts with water. And here the difference is in the atom carrying the charge. Again, right? But so in one case, we have an oxygen carrying the charge. In the other case, we have the nitrogen atom carrying the charge. Now, if you remember your periodic trends, some stuff doesn't go away, they're about the same size, right? Oxygen and nitrogen really almost exactly the same size. So the difference is not in the size of the ion, but they are different in terms of their electronegativity. Oxygen is much more electronegative than nitrogen. And so what does that mean for us? Well, electronegativity electronegativity is a matter of an atom's ability to hold on to electrons or to attract electrons to itself. And so you can imagine that the more when an atom has a high electronegativity, it is better able to hold on to its electrons. It's more, I'm using all these sort of qualitative words, but it's almost like it's more comfortable holding on to those electrons, and so it makes them less reactive. So increased electronegativity, again, means increased stability for the conjugate base. All right. So that is the second difference, but both of those have to do with the atom carrying the charge. All right. So size of the atom carrying the charge or electronegativity carrying the charge. And that works for a lot of cases, but there's a lot of other cases where there are differences. Now, if we look at the chlorine oxyacids here, well, so perchloric acid is strong. Chloric acid is pretty strong, actually, but the other ones are weak. And the question is, well, is there really where's the source of the difference between these? And so we're going to look at these ones and try and figure out where the difference is. So if I have, say, HClO4 in water, right? So whenever I ask you, so let's say a classic example of this question is like, I would say, well, consider HClO4 and HClO3. Why is HClO4 a stronger acid? So the first thing you should always be doing is writing out an equation for your acid reacting with water, because what we want to look at is the conjugate base. And as soon as the conjugate base has more than one atom in it, you need to look at its Lewis structure. Okay, so in both cases here, the conjugate base is polyatomic, right? So now this is something I can't emphasize enough, all right, is that the arguments, the reasons behind differences in acidity are structural reasons, which means if you are going to answer these questions, you must answer the questions using structures. It means you need to draw pictures, all right? There's no exceptions. There's no way to properly answer this without structures. If you're going to try and describe structures, you're wasting your words, and in an exam setting, you're wasting your time. You need to draw. So let's look at our conjugate bases. So we have the perchlorate ion, and then we have the chlorate ion. So we have now, the way we're going to do this is we're going to look at the factors that went into that that we know about. So the first thing that we looked at were, so the first two differences were related to the atom that we were looking at, the atom carrying the charge, right? And the atom had size and electronegativity, right? And so if we look at these conjugate bases, remember the size refers to the size of the atom carrying the charge. So is there a difference in the size, in fact, or electronegativity of the atoms carrying the charge in this case? And the answer is no, because it's oxygen in both cases. So there's no difference here, right? They're the same. Well, it turns out that the next thing, and remember, the idea here is we are either trying to contain a charge, or, and by contain, actually, I don't mean contain. What we're actually trying to do is stabilize a charge, either by having an atom with a lot of electronegativity or by spreading it out as much as possible. And one of the ways in which we can spread an electrical charge out is with resonance. So actually, I'll switch. I have a picture of this. So if we look at the conjugate bases for the different ions, now what we see is that in the perchlorate ion, and as we go down, we see that the charge density is lower and lower, right? Basically, and the difference here is that, in fact, we can draw more resonance contributors for some of the ions rather than others. So, for example, the hypochlorite ion here, there's no resonance possible, and so we have a very high charge density on the oxygen. For the chlorite ion, there's a little bit of resonance, so the charge density is somewhat decreased on the oxygens, right? But then as we can draw more resonance, the charge density decreases. And as the charge density decreases, we increase the stability, right? And so that's the next factor, is resonance. Now, if you're going to make arguments about resonance, again, you've got to draw the conjugate base, and you should be drawing resonance contributors in order to justify your point. So the next thing that we're going to look at is resonance. A classic example of this are acids versus alcohols. All right, so here this is acetic acid. Just a reminder what the structure looks like. So acetic acid is CH3. That, and this is alcohol, similar, but all right. Now, again, in both cases, so acetic acid is acidic, right? It has a pKa of 4.8 about, and ethanol here is not acidic with a pKa of 16. And when we look at their conjugate bases, they both have, again, the negative charge on an oxygen. So there's no difference between the size and the electronegativity. But there is a significant difference because of the resonance, right? In the case of the acetate ion here, the negative charge is spread evenly between the two oxygens. And so the charge density is lower. But in here, the charge is completely localized on the oxygen. So that is what makes the difference. So the next difference that we're going to look at is resonance. So now we have the atom. So the first thing is we look at the atom carrying the charge, and we look for differences there, size and electronegativity. The next thing is resonance. All right. And if the more resonance structures you can draw, the more the charge is delocalized, the more stable the conjugate base. After that, we get to kind of the last factor. So, for example, if we look at these three compounds. Now, one of the things I really want to point out is that these types of problems are very much like, in terms of how you should approach them, they are like math problems, right? Obviously, they're not calculation based. But what I mean is that when you do any kind of math problem, right, if you look at an equation, you don't know the answer. I mean, aside from, basic math, or if you're much, much better at math than me. But let's say you have even just a derivation or an integration or even complex algebra. The way you get to the answer is actually by solving the problem, by working it out on paper. You don't know the answer. You don't just sit and think, at least most people, I think, and then come up with the answer and write it down. And the mistake that a lot of people make when they're approaching this type of problem is to think that they can simply approach the problem and just think about it and then try and write down an answer. But in fact, that's the wrong thing. What you should be doing is, you have to write it down in order to arrive at the solution. You don't start writing when you know the answer. You start writing in order to know the answer. All right. So, for example, if I want to figure out why these three acids have different pKa's, I can't tell just by looking. I need to solve the problem. So the first step is always going to be to write out a dissociation with a reaction with water and come up with its conjugate base. And remember from your NYB that a conjugate base is just when you take off one hydrogen atom. So then, the acid reacts with water and we remove a hydrogen. And just so we're clear, when it's these kinds of acids that are known as carboxylic acids, it's always this one. Okay. And we can talk about why that is actually in a minute. But for now, I'm just going to tell you that it's always this one. So if I draw the conjugate bases of each of these, I'm going to draw them in a more expanded form. All right. So the question is, where are the differences in these acids or in the conjugate bases? So we said the first bit of analysis that we were going to do is the atom, right? So remember the atom is size and electronegativity. But in each case, the negative charge is on the same atom, right? So there's no difference. What about resonance? So that's the next thing we're going to look at. Is there a difference in resonance between these compounds? Again, the answer is no. So if you want to figure out where the resonance is, the first thing always is to look for what we call conjugation, which means I've got, say, a lone pair or a negative charge, and then a single bond, and then typically a multiple bond. And all of them have this bit here. The rest of the molecule is all single bonds, and they all have the same resonance. So again, no difference. So we need to find something else. So this is the next item in our hierarchy, which is something called the inductive effect. So really, we're going to look at three elements, and you can think about them just ARI, all right? The atom, resonance, inductive effect. All right, and now I'm going to explain to you what the inductive effect is. So the inductive effect. We're going to use this one here, formic acid or formate ion, actually, in this case, as our sort of standard, all right? Because hydrogen is sort of the relative zero in chemistry, right? So basically nothing going on. All right. Now, instead, let's compare that to, and if you notice, so there is a difference in the pKa's, right? The CH3 group here is more acidic, and this one here is less acidic. So let's start with compare it to acetic acid or the acetate ion. Why is this less stable? than this, right? And we know it's less stable by looking at the pKa's, right? So this is less stable, right? And how come? So when it came to things like the overall polarity of a molecule and intermolecular forces, we said that the carbon-hydrogen bond is nonpolar. And that's essentially true, but only sort of, right? The carbon-hydrogen bond, so carbon has an electronegativity of 2.5, right? Yeah, and hydrogen has an electronegativity of 2.1, which means that the difference in electronegativity of the CH bond is 0.4, which is right on the border of polar and not polar. So in fact, the carbon-hydrogen bond is a very, very little bit polar. And what's interesting is that it's polar this way, just a little bit. Now, because of the complexity typically of organic molecules with lots of carbons and hydrogens, this little bit of polarity, one, is small, and also typically all cancels out because the molecules are kind of moving all over the place. But in a very hyperlocal internal context, it matters, right? If the carbon is slightly more electronegative than the hydrogen, that means there's a very small partial negative here, and each of these hydrogens is partially positive. Well, so what, right? Why does this matter at all for us? Well, the reason it matters is I want you to imagine, what color am I going to use? I guess I'll use orange. All right. That we know there's resonance here, right? So the electron cloud is kind of dispersed. It's kind of spread out over this whole space, kind of like this, right? This is how the negative charge is spread. And so the orange is negative charge. But here, we've got this cloud of negative charge with another partial negative charge next to it, right? And so what does that do? Well, it means the negative charge is more localized on the oxygen atoms, right? In this case, because, right, the partial negative on carbon so the partial negative on the carbon repels this electron cloud and makes it less spread out. Okay, and if it's less spread out, it's more reactive. All right, and more reactive means less stable. All right, so the inductive effect is essentially about partial charges adjacent to the main acidity site of the molecule. Remember that typically the first step, whether it's the size or the electronegativity of the atom, those are those are the most important, right? What I'm presenting to you here is a hierarchy, right? So as soon as you find a difference, you can stop because that's usually where we can explain the difference. But as we keep going, right? So, right, when we started, say here, right, between F minus and I minus, there's a difference in the atom carrying the charge. Full stop, right? But there are acids that are more complicated than, say, just this. So then we look at, say, these two, right? And in these two here, the difference between them is not in the atom carrying the charge. Right? The atom carrying the charge is the same in both cases. So now we need to find a different difference. And in this case, the difference turns out to be resonance. And then that's enough. We can just stop. Sometimes, though, we have to dig a little bit deeper. In all three of these cases, well, when we look at their conjugate bases, the atom carrying the charge is the same. Again, it's always oxygen. And the resonance is the same in all three as well, because they all have this arrangement of atoms. They all have the same resonance. So again, full stop. All right. So we have to look for the next difference between them, and that is in the larger, then we have to look sort of to the rest of the molecule now. The inductive effect works in both ways, though. All right. So we see here, if we get a partial negative near the acid site, what does that do? Well, we see what that does, but it works the other way in that if we get a partial positive near the acid site, so if we took the case of the third molecule we were studying, which is this one here. Right now here, the chlorine is more electronegative than the carbon, right? And so now we end up with a partial positive charge near the acid site. Here we have, right, a delta plus near the electron cloud. The acids, and we can also call it the acid site. And so what does that mean? Well, we have our electron cloud like in the other cases, but now, so this is a cloud of negative charge, right? And there's a partial positive, and so opposite charges attract each other. A little bit something like that maybe happens, right? So the electron cloud, so the negative charge, if we will, so the inductive effect is about what's happening not right where the negative charge is, but next to it, adjacent to it. So I'll give you some other examples of how this works. All right, so we saw here, right, that we have the possibility for either an inductive effect that makes the acid weaker if we get a negative charge on this carbon, or an inductive effect that makes it a stronger acid by putting a partial positive on this atom. And then the inductive effect, there's a few parts of it. The first thing is that it depends on proximity, right? It's very, very local effect, right? So here we can see the chlorine is on the carbon atom right next to the acid site, and it has a pretty strong effect. The further away we move the chlorine from that site, the less of an impact it has. It becomes less and less significant in terms of the overall acidity of the molecule, right? So those polar bonds have to be close to wherever the acid site is. The other thing is that the inductive effect is additive. So, right, if I have one chlorine, it has some impact. If I have another chlorine atom, it has a bigger impact. And then if I have all three chlorines there, then it becomes an even bigger impact, right? So that is and then obviously the polarity, right? So the more electronegative the atom is, the bigger the effect is. And so that really covers it. So what I want to do with the rest of the class today is actually just some reviews. So I want to summarize, all right? The way we're going to analyze, all right, So again, this is the kinds of things that we're always going to be doing, or that I will be asking you to do, are comparative analyses. All right. It's going to mean I'm going to give you 2 or more acidic compounds, and I'm going to ask you to analyze them and say, well, how come this one is more acidic than that one? So the first thing that we're always going to do is draw the conjugate base. Always. So this means remove the acidic hydrogen. So that means, like, if we have HX, I don't know, like if we had HNO3, for example. Right, so these would be the acidic hydrogens. Right, those are 3 sort of really good examples of, because we want to always be analyzing the conjugate base. And so that's the first thing, is draw the conjugate base. And then we do the ARI. And it's always about differences. So in the atom carrying the charge, and it's the atom, right? So, and they are in size or electronegativity. After that, then it's differences in resonance. And then it's differences in inductive effect. So the first 2 that we are going to look at are H2SE versus H2O. So again, the first thing that we do is figure out what the conjugate base is and draw it. So we're going to do, so H2SE plus water gives us HSE minus and H3O plus. And obviously water, well, gives us OH minus plus H3O plus. So we are going to be comparing this against this. All right. So now I'm going to write, so HSE minus, and then like that. So the first thing I'm going to compare is, so I have ARI, right? The atom resonance inductive effect. So in this case, I look at, is there a difference in the atom carrying the charge? And clearly there is. They are different atoms, right? And the 2 factors that we look at are size and electronegativity. If that hasn't been clear to you guys yet already, size size wins, I guess. Size matters most in this argument. Is there a difference in the size of the atoms carrying the charge? Yes. No, the answer is yes, right? So if we looked at a periodic table, oxygen, sulfur, selenium. Selenium is bigger than oxygen. All right. So Se is bigger than O. Se minus is more stable. That's it. Then the discussion's over, right? If I found a difference at the level of the atom carrying the charge, then I stop. That's it, right? And so this is where, whenever we talk about, like things that matter in terms of, is what's on the final or what's on a test as well, you need to know your periodic trends in order to answer this, right? So am I going to, well, now the test is done, but like, you need to remember all your stuff from previously because it builds on all of it. All right, so that's a simple one. Let's look at a different example. All right, so now we have two, HNO3 and HNO2. I'm going to get you guys started and then see if you can figure out how to proceed. So again, I have HNO3 reacting with water to give me NO3 minus and H3 plus. And then I have HNO2 reacting with water to give me NO2 minus H2 plus. So I'm going to be comparing nitrate and nitrite. Now these are polyatomic, so I need to draw structures. So I'm going to draw the Lewis diagrams. Now I happen to know these ones. It's the best of them. Yeah, no, this one's fine. Okay, so again, I'm going to say, well, A, so under these, and I. So let's work our way down the list. Are there differences in the atom carrying the charge between the two acids? There, it's oxygen, so no difference. So then the next question is resonance. Well, I made a little table, kind of a pseudo table here, but honestly, that's not really enough place to do the work. All right, if you're going to figure out if there's differences in the resonance, you're going to have to draw. So if I look at the NO2 ion, right, well, I can draw one other resonance contributor. In contrast, if I look at the nitrate ion, now nitrate is one we've studied in class before, and so you may remember that there are in fact 3 resonance contributors to nitrate ion. So this one has 2 contributors. This one has 3. So the charge is more spread out in the nitrate ion. So NO3 is more stable. This is the way. And if the conjugate base is more stable, then HNO3 is stronger. And since we found the difference at the level of resonance, we don't need to go any further. We can stop there.